Welcome to this fascinating journey into the world of Cnidaria. Today, we are going to explore some of the ocean's most beautiful yet dangerous creatures. From the vibrant coral reefs that support immense marine life to the stinging jellyfish that float gracefully in the currents, these animals are truly marvels of nature. We will uncover how they are built, why they are so important to both ecology and modern medicine, and even dive into the incredible physics behind their microscopic, venomous harpoons. Let us get started. To begin our exploration, imagine swimming in the ocean and suddenly feeling a sharp, burning sting, or looking through a glass-bottom boat at a colorful coral reef. Both of these vastly different experiences are brought to you by the exact same group of animals, known as Cnidaria. This phylum includes jellyfish, sea anemones, and corals. While they might look incredibly diverse, at their core, they are essentially simple, jelly-like bags with a mouth surrounded by stinging tentacles. They act as beautiful but dangerous living traps, using specialized harpoon-like cells to catch their food. By the end of our lesson, you will understand exactly how these seemingly simple creatures manage to be top predators in their microenvironments. Now that we know what cnidarians are, let us look at how their bodies are constructed. These are primarily marine invertebrates that exhibit a tissue level of organization. This means their cells work together as distinct tissues, but they do not possess true complex organs, like a heart or a brain. Furthermore, cnidarians are diploblastic. This is a crucial biological term, meaning their bodies are built from only two fundamental cell layers. There is an outer layer, called the epidermis, and an inner layer called the gastrodermis. Separating these two living tissue layers is a non-cellular jelly-like substance known as mesoglia, which gives animals like jellyfish their characteristic squishy texture. Building on their unique body plan, let us examine how cnidarians interact with their environment. They possess radial symmetry, meaning their body parts are arranged around a central axis, much like the spokes of a bicycle wheel. Because they drift or stay attached to surfaces, this symmetry allows them to sense food or danger from any direction equally well. When they do catch prey, they use an incomplete digestive system. This means they have only a single opening that serves as both the mouth and the anus. Food enters this opening and goes into a central space known as the gastrovascular cavity, where digestion takes place, and waste is expelled back out through the exact same opening. You might wonder why we should care about these simple, brainless creatures floating in the sea. First and foremost, they are the master builders of the ocean. Corals create massive reef ecosystems that support about 25% of all marine life on Earth. Without them, coastal ecosystems would completely collapse. Beyond ecology, cnidarians have revolutionized modern medicine and biology. The green fluorescent protein, originally discovered in jellyfish, is now used worldwide by scientists to track cancer cells and study complex genetics. Furthermore, understanding their unique stinging mechanism helps us develop better treatments for marine envenomation and even inspires microscopic, needle-free drug delivery systems for human medicine. Having seen their global importance, let us zoom in on their most defining and deadly feature, the sting. To understand how a tiny microscopic jellyfish cell can pierce tough human skin, we have to look at its stinging capsule, known as the nematocyst. The capsule builds up an immense internal pressure by actively pumping ions inside.
This high concentration of ions forcefully draws water into the capsule through a process called osmosis. This rapid influx of water creates a biological spring that is loaded and ready to explode the moment a fish or a human brushes against it. It is a perfect example of biology utilizing pure physics to create a deadly weapon.
Now that we understand the biological mechanism of the nematocyst, let us look at the mathematics behind this explosive force. We can calculate this immense osmotic pressure using the Van't Hoff equation from physical chemistry. The formula is pi equals I times C times R times T. Here, pi represents the osmotic pressure inside the capsule. The symbol I is the Van't Hoff factor, representing the number of particles the solute splits into. The variable C is the molar concentration of the solutes inside the capsule. R is the ideal gas constant, and T is the absolute temperature. This formula tells us that as the concentration of ions, C, increases inside the cell, the explosive pressure, pi, increases proportionally, creating a highly pressurized biological bomb. Let us put this formula into practice with a concrete example. Imagine a sea anemone's nematocyst capsule has a solute concentration of 6.0 moles per liter. We are given a Van't Hoff factor of 1, an ocean temperature of 298 Kelvin, and a gas constant of 0.0821. We need to find the pressure that drives the harpoon out of the cell. We substitute these exact values into our osmotic pressure equation. Multiplying 1 by 6.0 by the gas constant and by the temperature gives us our result. The final answer is approximately 146.6 atmospheres of pressure. This is more than 100 times the pressure in a car tire, explaining the explosive, bullet-like speed of the sting. Now that we have calculated the massive internal pressure, let us look at the actual impact on the victim's skin. We know from basic physics that pressure is defined as force divided by area. Therefore, to find the absolute physical force pushing the tiny needle into the skin, we must multiply the pressure by the area. The formula is F equals P times A. In this equation, F represents the total force, measured in newtons. The variable P stands for the pressure in pascals, which is the driving force behind the sting. Finally, A represents the incredibly tiny cross-sectional area of the needle tip in square meters. By multiplying the massive pressure by the microscopic area, we can isolate the force variable to see what the skin actually feels. Let us see exactly how much force this microscopic harpoon delivers. We are given a driving pressure of 15 million pascals, which is roughly equivalent to the 150 atmospheres we just calculated. The incredibly sharp tip of the stylet has a microscopic cross-sectional area of 0.00000000002 square meters. We substitute these values into our force equation, balancing a very large pressure number against a very small area number. The calculated force is 0.000003 newtons. While this number looks incredibly small to us, remember, it is concentrated on a point measured in nanometers. This creates enough localized stress to easily puncture human skin and inject venom. Having explored the physics of their sting, let us look at how scientists group these fascinating animals. Phylum Cnidaria is divided into 4 main classes based on their life cycles and body forms. The first class is Hydrozoa.
This group includes small, often freshwater organisms like the hydra, as well as complex floating marine colonies like the infamous Portuguese man-o'-war. The second class is Scyphozoa. These are the true jellyfish that you often see washed up on the beach. Scyphozoans are characterized by spending the vast majority of their lives as free-swimming, umbrella-shaped medusae, drifting through the ocean currents.
Continuing with our classification, the third class is Anthozoa. This group includes the beautiful sea anemones and the reef-building corals. Unlike the jellyfish, anthozoans completely lack a swimming medusa stage. Instead, they leave their entire lives attached to the seafloor as stationary, tubular polyps. Finally, we have class Cubozoa, commonly known as the box jellyfish. As their name suggests, they are cube-shaped. Interestingly, they possess complex eyes that allow them to actively hunt, and they carry some of the most deadly venom on the planet, making them highly dangerous to humans. Let us visualize the two fundamental body plans we just discussed. On the screen, you see a clear comparison between the polyp and the medusa forms. On the left is the polyp, typical of corals and anemones. Notice how its base is attached to the substrate, with its mouth and tentacles facing upwards to catch falling debris or passing prey. On the right is the medusa, typical of true jellyfish, which looks like an umbrella with the mouth and tentacles pointing downwards. In both cross-sections, you can clearly see the outer epidermis, the inner gastrodermis, the thick jelly-like mesoglia in between, and the large central gastrovascular cavity where digestion occurs. We have covered a lot of ground today, so let us review the most important ideas. First, cnidarians are simple yet incredibly successful animals that rely on a two-layered diploblastic body plan and radial symmetry to survive. Second, their defining feature is the cnidocyte, a marvel of biological engineering that uses extreme osmotic pressure to fire venomous harpoons into their prey. Finally, they are classified into four main groups: Hydrazoa, Scyphozoa, Anthozoa, and Cubozoa, based on whether they live as stationary polyps or swimming medusae. Understanding these creatures gives us profound insights into marine ecosystems and the incredible physics hidden within microscopic cells. Great job following along.